We present a convex formulation of compliant contact suitable for robotics simulation, planning, and control. We introduce a number of novel contributions. Our formulation eliminates contact constraints analytically to write an unconstrained convex problem on velocities only. We put a strong emphasis on the rigorous characterization of the method and the physical validity of the convex approximation of contact. In addition, we present the semi-analytic primal solver, or SAP solver for short, that converges globally and warm starts effectively, enabling the simulation of complex multi-body systems with frictional contact at interactive rates. We make the implementation of our method publicly available in the open source robotics toolkit Drake. Specified by physical parameters, our model can be described in clear physical terms instead of abstract optimization-specific terminology. This permits not only the modeling of compliant point contact, but also more sophisticated model of compliant surface patches. The video shows a contact-rich manipulation of the pulse of a spatula with a soft bubble gripper by controlling the grasping force. Contact surface patches are colored by contact pressure. Here, we use a simple example to illustrate our model, though the discussion applies in general to complex multi-body systems. In this example, a sphere is in contact with the compliant ground with a penetration distance of phi. It has velocity with horizontal component Vt and normal component Vn. During stiction, our formulation recovers a linear spring damper model of compliance. Friction is regularized and acts like high viscosity fluid, opposing the small amount of slip. In our paper, we show how our solver regularizes friction to minimize drift and achieves stiction with high accuracy to simulate demanding manipulation tasks. During sliding, normal forces still follow a spring damper law, but the convex approximation introduces a spurious offset proportional to the slip velocity. For robotics applications such as manipulation and locomotion, slip velocities are usually low enough such that this offset is negligible. Moreover, since our formulation obeys Coulomb's law of friction and the principle of maximum dissipation, it can properly resolve stick-slip transitions. We exploit sparsity structures to solve medium-sized problems at interactive rates. In this example, 120 rigid objects are dropped into a pile on the ground, generating up to 600 contact points. We evaluate the performance of our SAP solver against the commercial solver Gurobi, an industry standard, and against the open-source geodesic IPM solver from Performant 2020. The SAP solver can perform up to 50 times faster than Gurobi in small problems with about 10 bodies and up to 10 times faster for larger problems involving hundreds of bodies. The SAP solver is about 2 to 5 times faster than geodesic IPM while significantly more robust and accurate. Our time-stepping scheme is based on the theta method, and we show that our method preserves the usual property of the time-stepping scheme even through frictional contact. In the spring cylinder system shown in the video, the cylinder is set free to oscillate as it makes rolling contact with the ground. The animation shows the total mechanical energy of the system, which should be conserved with rolling friction. Implicit Euler quickly dissipates the energy of the system, while symplectic Euler bounces energy oscillations but doesn't eliminate them completely. The midpoint rule introduces negligible dissipation, and in our paper, we show that it achieves second-order accuracy even in the case with frictional contact. Here, we simulate a challenging dual-arm manipulation task involving two Kuka-Iwa arms outfitted with 16 degrees of freedom anthropomorphic Allegro hands. The robot is tasked with opening a jar full of marbles, pouring its contents into a bowl, closing the lid, and placing the empty jar back in place. This is a computationally intensive simulation with 160 degrees of freedom and hundreds of contact constraints per time step. The SAP solver warm starts very effectively, requiring only 3 to 4 iterations per time step on average. Thank you for watching, and we encourage you to read the full paper for details.